for those who attended my talk, you'll notice that I didn't talk about his work. I showed you a slide. So here's the full details about the natural shade system.
Yes, so I will talk about the Lacroche system, which is a system for proof-checking mathematical texts in controlled natural language. So, okay, so we developed as part of the Lacroche project, which is an interdisciplinary project at the universities of Bonn and of Duisburg-Essen, which studies the language and the reasoning of mathematics from the perspectives of logic and linguistics. And the main goals of Lacroche are to develop a controlled natural language for mathematical texts. So this is a formally defined subset of the natural language of mathematics, and to implement a system, an Lacroche system, which can verify texts written in this controlled natural language. So just to give you an idea about what this input language looks like. So basically, from this example text, it's a language that a normal mathematician can read without having to learn like a separate formal language. It just reads like normal mathematical text, but it's a formally defined fragment of the language that mathematicians use. So it has a formal semantics, and the Lacroche system can check that text written in this language actually is the correct proof. Correctness can be defined according to the semantics. So okay, so for checking the correctness, we have this proof checking algorithm, which works through the text and keeps track of a list of first of a formula which are considered true at the moment or at the point in the text, and I call these formally premises. So they come from like axioms, definitions, previously established facts. So the premises gets continuously updated during the verification, and each new assertion in the proof is checked by the ATP based on the currently active premises. So just a simple example here. So when you have so of course this kind of example would only work in the Lacroche system if you have like some previous text which introduces like axioms and definitions needed for checking this. So as in here you have this premises gamma where there's this previous information already in there. Then you start with an assumption, suppose n is even, so you add this even n to your premise list, and then you have to establish this existential statement like this. Now the interesting thing here in this example is after you establish the existential statement, okay, you can add it to your premise list, but when you add it to your premise list, you drop the existential quantifier, so you scrollamize the fact that you've established when adding it to the premise list. That is necessary here because, well, basically we have here a special, I will talk about this later. Is it in the next slide already? But this is, we'll talk about that. One thing that I want to say about this proof-checking algorithm is that, even the facts or even the sentences that don't have to be checked like assumptions, they still have to be processed in some way in order to produce this premise from them. And the way it's implemented is that there is like a general procedure for processing the text, and it has two modes. There's like the check mode and the no check mode. So the check mode you have to check everything that you process, and in the no check mode you just produce the premises that you add to your premises without checking anything. So it's called the no check mode. So it's used for assumptions, but it's also used like when you have like subformulas of a negation. For example, you process this phi, but you don't want to check phi, you want to check not phi. So you process the phi in the no check mode, and then produce the formal representation of it, and then add the negation to it. So you will see later why I do it in this way with this check mode and no check mode. of course, for this proof checking algorithm, we have shown it to be sound and complete. Okay. So this is what the system looks like. You can type in this text like this with well, LaTeX notation for the formulas, and then you can press and check, and then it will go through it. And then every sentence that has to be checked will be colored either green, orange, or red, where green just means okay, was checked correctly. Orange means it was also checked correctly, but some of the premises that, well, actually the conclusion was not used in the checking because the premises were inconsistent. Yeah, then you can write everything. You really only want this orange color in proof of completion. If you have an auto rejection, that's a sign that something is wrong. Yeah, so here it's okay because it's in the proof of completion. And then red means it couldn't be established. So I just want to, just as an example, I'll show you like empty set. In empty set, of course, meaningful conditions of empty set, of course, you can't establish that. Okay, so now I will talk about some interesting theoretical aspects that I had to cope with in order to, well, in the development of this approach system. So the first one I will talk about is dynamic quantification. So yeah, now I come back to this example. So here you have this extension statement. There is a case such as n equals 2k. And in the next sentence you still talk about k. Yeah, you say that an n squared equals 4k squared. Now that's a very natural thing to do in mathematical text. It's also very natural in general in natural language. But actually, if you think about it in first order logic, it's kind of weird because you've got like an extension statement. There is a k such that something holds, and so the scope of k is like ends here. And then you talk about k after the scope of the extension quantifier. And how can that be meaningful? Well, it is meaningful in natural language, and it's actually, I mean, it's something that linguists have studied intensely since the 1980s at least, and they call it the dynamic nature of quantification in natural language. Another example of this you can see here: if the space X retracts onto subspace A, well then this homomorphism induced by the fusion I of A to X is injective. Now the weird thing here is if you translate the space X retracts onto a subspace A, normally if you have this sentence in isolation, you would have to translate it with extension quantifiers. Yeah? If you have the whole thing, you will actually have to use universal quantifiers so that you can still talk about X and A on the right hand side. Also, you can do that. Now that's okay. As you can see from this, is like a real example from a math textbook. So mathematicians actually write things like that, and linguists have developed this dynamic predicate logic as a solution to this problem. So the standard example you find in the linguistic literature is a donkey sentence. If a farmer owns a donkey, he beats it. So here you see the same problem. You have to translate this in first order predicate logic with the universal quantifier, even though if you just had this farmer owns a donkey, you would use extension quantifiers. So somehow you can't use the translation of the subclause, which would be with extension quantifiers, when you should say the complete sentence that contains the subclause. You have to then change the quantifier. Whereas then there's this dynamic predicate logic, which is a modification of standard first order logic, which basically has the same syntax but different semantics, different binder properties, how variables are bound. So there you can actually write it like this, so you can say, yeah, there is a farmer who owns a donkey. This whole thing implies that, well, the farmer X beats the donkey Y. Yeah? Now in standard logic, these X and Y would be just free variables, so this wouldn't even be a sentence. But in EPL, yeah, the semantics and the bindings we define in such a way that this is a sentence and it is equivalent to this one, so you can use it as a translation.
Are the brackets really?
The brackets really close here. So this is where the scope, like the syntactical scope of the extension quantifier really ends here. But the binding is defined in such a way that extension quantifiers can bind variables outside their scope. Yeah. I'm not going to go into the details of how this is defined. You can do it in the literature. It's not that talk at the linguistics where I explain some of the details of this. Okay. And now, yeah, one interesting feature of the language of mathematics is what I call implicit dynamic function introduction. So here's a real example of this. Suppose that for each vertex v of k, there's a vertex g of b of l that satisfies the property. Then g is a simplicial map. It's a property. So here it's a bit weird. Yeah, you can say for each vertex v there is a vertex g of v. So like after a quantifier you have a complex term. Like normally in formal languages you expect a variable after a quantifier, but that in the natural languages mathematicians use it. But you can even have complex terms after quantifiers, and then by doing that you can kind of like implicitly introduce this function g. So this first sentence, by using this concept for every v there is a g of v, implicitly introduce g, and can talk about it in the next sentence. Now, as far as I know, no one has realized this phenomenon before, and so I proposed a solution or like a formal modeling of this phenomenon in an extension of dynamic predicate logic, which I call higher order dynamic predicate logic. So I briefly sketch this logic. Well, yeah, in this logic you can have complex terms after quantifiers. So you can write a formula like for all x there's an fx, such as rx, fx, and the semantics is defined in such a way that this formula has the same truth condition as for all x as a y, such as rxy. But in general, in dynamic logics, truth condition is not all there is to the meaning of formulas. So even though they have the same truth conditions, the first one kind of introduces f to the context, and the second one doesn't. So that's like the difference in meaning they have. So the third one is the first one is actually equivalent to the third one because it also introduces this f dynamically. And in the proof checking, it's when you have a sentence like this, for every v that's a g of v, when you prove it, well, okay, you add this assumption that v is a vertex to your premise list, and then you have to establish, okay, there's a vertex g of v. Okay, in order to give this thing to normal ATP, you have to write it like this as a w. Yeah, so you write w instead of g of v. So that's when you want to prove it. But after you've established it, you kind of scolemize what you've proven. So actually, since v is like a variable that doesn't occur in gamma, you've actually established that gamma entails that for all v, vertex v implies this extension statements, and then if you scolemize that, it's an extension statement inside the scope of the universal quantifier for all v. You get this one for all v, and then instead of w, you can write like in the scolomized form g of v, right? Because the g is your scolem function. But now the name of the scolem function that is introduced here is of course chosen in such a way that it coincides with the name that the user used actually in the original input text, so that when the user then in the next sentence writes something about g, well, that's actually meaningful. It has, it's the same function as it has. Yeah. So what the user does actually, well, apart from allowing the user to use like a natural form of expression that mathematicians use in their text, it also actually has some use in that the theorem prover now does not need to prove the existence of a function. Yeah, there's no proof obligation where you have to prove something like there is a function f, which might be like a bit tricky to prove anyway. But nevertheless, the existence may be assumed after. So after you prove this that there is a vertex w, then through this colonization, then the existence of this g is assumed in the premise list, even though you didn't prove the existence explicitly. Yeah, I mean, with colonization. Okay, this is just saying that similarly, in this example, sentence that I showed you before would be proof checked in the same way as this one, which has the same truth conditions, but then the premise you add to your premise list would be the same one as if you had proved this one. Okay, so one more feature of the language of mathematics that I want to show you is undefined terms and presuppositions. Okay, so you can have potentially undefined terms in mathematical text, like 1 over x, it's undefined if x equals 0. And such terms arise, of course, because of partial functions. And, okay, I mean, mathematicians would never write 1 over 0 in their text, but they do write things like 1 over x, and then, of course, one has to be careful about what value x can take. So it's a problem because x is a free variable. Yes, it's like an ungrounded term here as the argument of this partial function. So first order logic has no means for handling partial functions and it's such potentially undefined terms. Well, there have been proposed various solutions to this problem, but we make use of presupposition theory from formal linguistics for solving this problem. So, yeah, in linguistics, presupposition of an utterance is an implicit assumption that is taken for granted when making the utterance, and yeah, normally the presupposition of an utterance is required to be true in order even to make sense of the utterance. So, examples of yeah, words that trigger presuppositions, so-called presupposition triggers, are, for example, well, the word the, when you say something like the King of France, this presupposes that there is a King of France. When you say something like I know that you did this, that presupposes that you did this. I mean that the presupposition is like of a different nature than just an asserted fact, yeah, because it even stays there when you negate a sentence. When you say I don't know, or he doesn't know that I did this, that still presupposes that I did it. It's like negated the sentence. So that's something special for presuppositions. So other words in natural language that have this like stop doing something, like if you stop beating your wife, presupposes, and even as a question, it presupposes that you beat your wife before, and the same with so, yeah, okay, so okay, most of these presupposition triggers are absent in mathematical texts, but some of them appear, like yeah, definite descriptions of expressions starting with the, of course, not uncommon in mathematical text. And then there is a special kind of presupposition trigger in mathematical text that doesn't occur outside language of mathematics, which is well, expressions that denote partial functions, like the division symbol or square root when you're looking at the real numbers. Okay, so how is these presuppositions treated in an approach system? So the basic idea, that's why I introduced this concept of the no-check mode before, is that presuppositions have to be checked even in the no-check mode. So, okay, before I said, like, for example, assumptions do not need to be checked, yeah? Assume that B contains square root y. Yeah? When you have something like this, I mean, the assumption that B contains square root y, you still don't need to check it. But the presupposition that y is non-negative, that has to be checked even though it's an assumption. So you check this y is non-negative, and then you add the assumption B contains square root y to premises without checking it. So also in the negation, B does not contain square root y. You check this presupposition, then you add the presupposition to your premises, and then you check the negated statement. Yeah? So the presupposition did not get negated. Yes, only the statement that gets negated, but the presupposition stays. Yeah, you check it without negating it, and then also you add it to your premises without negating it. Yeah? So that is treated differently to how normal assertions are treated. And yeah, so it turns out that this is a good way for treating undefined terms arising from partial function. I have a paper about this topic.
What is their negation in use?
Negation there?
Yeah.
That comes from this negation here.
Oh, sorry, no, it's not the same example.
Yeah, so yeah, it's a different sentence. Now you're saying B does not contain square root y. Yeah, so you're negating. In fact, I mean the negation operator. Also, like syntactically in the syntax tree of this natural language sentence, actually outside the scope of a negation is the whole sentence, but nevertheless the presupposition does not get negated because it's a presupposition, not part of the assertion. Okay, so to conclude, okay, we have developed a controlled natural language for mathematical text and implemented an approach system which can check the correctness of texts written in this language. And also, I mean, apart from the practical contribution to the mathematics project, it's also been interesting theoretical work linking mathematical logic to formal linguistics.
Partial functions occur a lot in formal verification, and there are many different solutions to it, and quite easy debate about which is the right approach. And it just occurred to me hearing you talk that you have a handle perhaps on how mathematicians naturally handle it, because you've got a particular approach, and you may or may not find that that works well in natural proofs that you encounter. And so it might be interesting to see how mathematicians implicitly handle this, because I don't think they think too much about how.
Well, I think
they kind of
they don't think too much about it, but by not thinking too much about it, it means that they actually treat it the way that they treat similar phenomena that occur in natural language in general. I mean, presuppositions are of course something that you have in natural language in general, and I think that mathematicians treat partial functions, I mean the domain conditions triggered by partial functions, they treat them like presuppositions, so the general theory of presuppositions that linguists have developed, I think, is quite useful to.
So you say there's evidence that this is the way that people naturally.
Yes. Yes. I have. Well, I mean, here I just presented a bit of a simplified version of it, because there's a further thing in presupposition theory which is called presupposition accommodation, which I can't talk about here. And that really, I mean, you really need that one to get a good treatment of these presuppositions. It's actually, this presupposition accommodation is also not yet implemented in the approach system, but I've got a paper about it where I explain in detail how one presupposition, like addition with this presupposition accommodation, and compare it to other approaches of treating partial functions in formalized mathematics, and conclude that this is like the most natural for a mathematician. It models best how the mathematician naturally uses.
By the way, you were claiming that this form of undefined term suffers very ordinary issues. How long? If you say, as your husband is also invited, that's still defined as well by marriage.
Yes. Yes, of course. Yeah, we wouldn't. Yeah, but you wouldn't say to a single person your husband when you know that person's unmarried. So that's that. Well, yeah, that's why I said when you know that this is unmarried. Michael?
How much is actually written in abortion?
How much is written? Okay, that's a good question. As part of my PhD project, I was mainly working with the Landau text, this Landau sozusagen the analysis, relational analysis text. And that one, in the current version of my approach, is only the first chapter that's working. In the previous version was also half of the second chapter. Then there is a beginning of Euclid's elements up to like fifth or sixth theorem in there, and there is now proof of the existence of infinitely many prime numbers, basically from piano arithmetic or from the facts that combining it with what is established in Landau from piano arithmetic, from the axioms of piano arithmetic. And then there are some toy examples, like this Raleigh 40 example that I showed you here is one of them, and there is it's actually a bit longer than the version I showed you here, and there is another toy example which is like some very basic proof theory, but not even not even quantifying over groups, just quantifying over the elements of the group, very basic stuff.
I really enjoyed this talk because I've used all the things that you've talked about in my own writing, and I felt guilty about all of them. I wanted to ask, do you think that any of these constructs that you've been talking about would also be useful in formal languages, or does it just not make sense in your opinion?
Yes, that's actually a very good question. I think, one should actually seriously consider when designing a formal language for example, for formal math. I mean, in order to making it more natural for users, I think it might actually be useful if one had constructs like these ones and treat it basically in the way that I showed here. Yeah, I mean, okay, but when you say formal language, maybe I think about something more like, even with a language that doesn't look like natural language, maybe you don't want to have these issues of disambiguation that I didn't really talk much about today, which of course are issues when you're doing something like this in a kind of natural language. Maybe you want to avoid this, but still want to get the goodies that I described here.
This is completely formal.
Sure.
But you could do like a formal language in the sense of one that doesn't superficially look like natural language and doesn't have the issues of disambiguation techniques, but still has the features that I described here today. I think that would be quite a sensible.
I just wanted to go back to the previous question. Do you have anyone else who's not a developer of the system using it to write proof?
Yes, I mean this infinitely many prime proof that I just mentioned is actually developed by a group of students who have been working with this system for some time now. So yes,
Because I think I might find it annoying to write something in this language, though I can see how it's very useful to have readable proofs. Redeemable proofs.
Yeah, I mean, of course, this controlled natural language approach, the naturality for writing is actually not that much higher than I mean, it's still like a similar effort to learn to write in this language as it is, or even might even be a bit more than to learn to write in a formal, really formal language. But of course, for the reader, the main advantage is really for the reader, at least currently. I mean, I have thought about approaches that would at least, you could kind of think about having a less strictly defined input language for writing the proofs, and only the axioms and definitions and theorems would have to be like in your strict controlled language, because there you really want to be sure that it has the meaning that you think it has. But for the proof, it wouldn't matter too much if you use like a less restricted language there, which might be misinterpreted sometimes, then the proof just wouldn't work. Or if it still works, then okay, then the system maybe has found another proof that you wrote out. Maybe that's not too much of a problem. So in that sense, one could think about having like a modified version of a Porsche where the language therefore for writing the proofs is less restricted, and then it would actually be even more natural for writing it.
Stop there. Thank you, Marcus. So the next talk in this series is from Mark Koza from the University in Bremen, and he's going to talk about math.
Well, actually, that's the title I promised before thinking. Let me start off slightly differently. I'm very happy to be here at the QED workshop. I haven't been invited to the first QED workshop in 1994, go to the second one. For some reason, I forget why. So I'm very happy to be here on the third one. QED is something that's kind of in the back of my mind very often. And I find it really influenced me a lot. So there's a slight disconnect between the title and the talk, which comes from the fact that I started thinking more about QED in the preparation of this talk, and did a couple of little exercises which were very rewarding for me. One of them was that I went back and reread the QED manifesto. Who else has done that in preparation? Very good. And I remember that in the year of my PhD at K94, the QED manifesto was very heavily discussed and created quite a stir. Inspired me, among other, greatly. Then there was the QED mailing list, which I was subscribed to, and I went through the exercise of rereading parts of that. And that's really fascinating. It's really nice. And just looking back, the question that Alan just asked about partial functions, that was heavily discussed in the mailing list. Types have been mentioned today. Does math need formalization, or is it really the other way around? That was never quite resolved. Funding, I mentioned, that was one of the things that was never, in any case, in any way resolved, except maybe for this Argonne workshop. And so, there's also this nastiest of all topics, which I think of as the root logic controversy, which takes, by the way, I've tried to count, takes up most of the mailing list as well. So let me summarize that discussion for you. Basically, everybody started out into the discussion with, please use my pet logic as the root logic. And some people said, please, and other people basically started flaming. And there was a big debate and no clear winner.